Hi everyone, this is Casey here. Today's video is about exponential growth and decay. I'm going to start off with a quick warm-up here just to get you thinking about how to solve problems of this style. I'm going to show you algebraically with the use of the calculator, and then if we get a chance, we'll also look at it graphically with the calculator. So this would be a problem that maybe you need to solve, and you want to solve for t. So I've already got it worked out here for you. So the first thing you're going to do is you're going to divide by 9. And now you've got just the e to the negative 0.2t on the right-hand side. And after you divide by 9, then you're going to rewrite it in log form using base e. So this becomes the natural log of 25 over 9 equals negative 0.2t. Now you're almost there. And you're going to put this final result into your calculator and divide. So you get natural log of 25 over 9 divided by negative 0.2. That's what t is equal to, and you just type it in to your calculator, being very careful of the parentheses, and you should get negative 5.108. So if you're not getting that as an answer when you try it on your own, my first thought would be that you didn't use parentheses correctly, or maybe you didn't type something in here in the argument correctly. Okay, so that's our warm-up. So then we're going to talk about the two different forms of the formula that we have. So the one on the left is what I would call the more scientific version of the formula, where it uses e. And then the one on the right is the more, algebraic, form of the equation, form of the exponential growth and decay model, I should say. And that's also what your calculator does. So when we do a regression model, which is something we're going to do in a few minutes here. So when we do regression on the calculator, your calculator only gives this format on the right, but you need to be able to also switch it to the form on the left. Calculus and science are going to use the one on the left. So one on the left, one of the reasons they use it is because it's specific, like you can pick out each piece of information. So A naught is the initial amount, K is the growth or decay rate, and T is time. Pretty straightforward. So I could give you those pieces of information, you just substitute it in. It's different on the right-hand side though. So the little a is still the initial amount, and x in this case is time. But notice if I compare the two equations, and sometimes it helps if I just compare them one above the other. So I'm going to write it like this, and then I'm going to write this one below it. So you can see that the a and the a naught are equal, and the t and the x are equal, which leaves us with this stuff in the middle to be equal. So B is not directly the growth or the decay model, or rate, sorry. B is actually equal to e to the kt, okay? So if you were given this model first and you wanted to translate it into the other form, you would have to solve for k, which would then be the natural log of b. So B is not the growth rate, the natural log of B is. Okay, you're going to need to be able to go back and forth between the two. This is probably the most important part to help you figure out how to go between the two. All right, the first example was actually worked out for you on your paper. So I just want to point out to you what was done, and then we're going to do another one that's similar. So this says that there was traces of burned wood along with ancient stone tools that were found at an archaeological dig. And they were found to contain approximately 1.67% of the original amount of carbon-14. So remember that carbon-14, they do that carbon-14 dating to help figure out how old something really old is. This is the important piece of it. And if you're in chemistry, you may have already worked with this. So the half-life of carbon-14 is 5,600 years. Half-life, and I think I'll type this over here for you. Half-life, well, that's not what I wanted. Let's try again. Is the amount of time it takes for some sort of, some element to decay to half of the starting amount, or any amount. So when we say half-life, it's literally, it took that amount of time to go from 50 to 25, or 100 to 50, or 1 to a half. Okay, it doesn't matter how much you start with, you're going to go to half after you're done, which is what's going on in this problem over here. So we don't actually know how much we started with. We just know that it takes 5,600 years to get to that half. So anytime you're asked to find a half-life, your best bet is to start off by putting a half on the left, and then, so let me remind you of the formula, right? We're using this formula. So a half is going to go in for the ending amount, and 1 is going in for the initial amount, because it doesn't matter how much I have, I'm still going to end up with half later on. So it's going to be a half equals 1 e to the, and then the time it takes to get to that is 5,600, and you're solving for k. So you do your natural log stuff, you get your k, and of course you're going to store it in the calculator. And I'm going to remind you how to do that on another problem in just a minute, but you're going to store it. And then you can see here, I actually typed k because I know I have k stored. And when I get to here, in this spot, I have two choices from here. I can graph it, or I can do the natural log again. So I didn't actually show you that middle step in here. So I would do the natural log of 0.0167 equals kt, and I'm dividing by k, which then gives me that very large number, which should make sense because we are at an archaeological dig. Okay, next one. So this problem is pretty similar. You have to do, it's like two parts. You have to first find the half-life, and then you have to find how much is left to get down to, how long it takes to get down to 10 grams. Okay, so strontium-90 is a radioactive material that decays according to this function. So it actually gave you the decay rate right here. What is the half-life of strontium? So it wants us to figure out how long will it take until the amount of strontium goes to half of where it started. So it's going to be the same setup as I talked about before. So you're going to take your equation and you're going to put 1 in for A naught. So 1 in for the initial amount and a half in for the ending amount. And I just didn't write the 1 there. But we're solving for T now, not K. So then second step, take it and rewrite it in log form, and then divide by that K value that's there, and you get 28.881 years. Okay. Now we're being asked to find something in terms of time this time. So we're given 40 grams initially. And we're ending with 10 grams, okay? So now we're gonna solve this. So I think I'll take out the calculator to remind you how to type everything in. I hope that we'll be able to see it well when I put it on the screen, because I wanna share, nope, I only want it to be part of the size. Okay, so I'm gonna put it over here. So I'm going to divide 10 by 40. 10 divided by 40. Of course, that happened. And then we are going to take and rewrite this in log form. And also divide that answer by that negative 0.244. Oops. 0.244, sorry. All right, let me bring that calculator back up. So natural log of that answer divided by negative 0.0244. So 56.815 is how long it will take. 56.815, and I feel like we were in years. Yes. Always label and always go to 3 decimal places unless it asks you to round to the nearest whatever, and then you round. All right, so here's the one where we're going to do regression. So it says a chemist has a 100-gram sample of radioactive material. He records the amount of radioactive material every week for 6 weeks to obtain the following data. So he starts with his initial amount, and then every week after he starts recording the data of how much was in there. We want to find an exponential regression equation in the form of y equals a times b to the x to match the data. Okay, so I'm going to show you how to do this, remind you how to do this. And remember, as we go through, to stop the video if you need to type things and copy things down. Okay, so the first thing you're going to want to do is enter the data in the lists. So to enter data in the list, you hit the stat button. And then you go to edit. So it's stat and then edit. And then in list 1, we're going to put the weeks. And in list 2, we're going to put the grams. So weeks, weight. Okay. So maybe pause and enter the data and then come back because I'm going to keep going. So now I have my data in here and I want to make sure that my stat plots are on and my y equals are good so that I can go ahead and graph this. So the first thing I'm going to do actually is go to my y equals and clear out anything that's in there because I don't want that to get confusing or accidentally stay there later on. So I'm going to get rid of the y equals. And then I'm going to turn my stat plots on. And I actually already knew that they were on because in my y equals, when I hit y equals, if this is darkened, the plots are on. Okay. But if I want to set them up specifically, I actually have to go to second y equals and go to the stat plots there, and I can see that they're on here. And this is where you can change everything. So for the most part, we're only going to use the scatter plot here. Most of the time, list 1 will be X1 and list 2 will be Y list will be L2. You can use any marking you want, any color you want, doesn't matter. If I can get it to change, which I cannot, I don't care that much. Okay. Now I'm going to set my window. So I know that my data goes from 0 to 6. So maybe going a little bit less than 0 and a little bit more than 6 would be helpful, especially if I'm going to have to solve something later on. So I'm just thinking ahead that maybe I'm going to need to know more than 7 weeks of data. Maybe I'm going to need to know 30 weeks of data. So I'm going to go ahead and put 30 in. I don't really remember, honestly, but I'm going to do that for now. I'm going to go by 2 on my x's. And then looking at my weight, that's my y's. So my largest number is 100. And if we go past 6 weeks, we're going to assume it's going to keep decaying. So the number is going to get smaller. So maybe I go a little bit bigger than 100 in my max. And then I'm going to just go to 0 on my y's. So this is my window. I'm going to hit graph. And then there's my data. Okay, so you can see that it is definitely doing an exponential regression shape in here. And you can kind of visualize that it's going to go down like this. Okay, so now I want to find that equation. I find the equation by doing regression. So I go to do regression, I go to stat and then over to calc. And calc has all the regression information. So like this is linear, quadratic, cubic, quartic, another linear. That's logarithmic. That's exponential, which is what we want. That one's a power. We probably won't use that one. And then logistic, we'll actually use that one as well, probably tomorrow. So we want the exponential. And we want to make sure when it comes up like this, that list 1 is in the X list and list 2 is in the Y list. List 1 in the X list, list 2 in the Y. I think that's what I said. And I want to store the equation that I find into Y1 so that I don't have to copy it over. So to store it, I go to vars, yvars, function, Y1. So now it's going to say store it into Y1, and then it says calculate, and I hit enter. If you, well, that was fast. If you have an older calculator, I'll show you in a second because it's actually on the screen how you need to type it in. I just need to scroll back up. All right, here is the answer where it's saying the initial amount is about 100.326, which remember it's calculating it based off of making an equation. So that's a pretty good match. And then we get this B value, which is less than 1, which makes sense because we're decaying. All right, if you have an older calculator that doesn't look like that, the the way you type it in, I want to go back so I can show you, should be like this. So you're going to still go to stat and still go to calc and then the exponential regression here. And then you're going to type in list 1, comma, list 2, comma, y1. And list 1 and list 2 are here above 1 and 2. And it'll show up on your screen like that with the commas, and then you hit enter and you find the same answer that way. Okay. All right, so we have our answer here. Now we want to rewrite it in this form. So to rewrite it in this form, remember that the A and the A naught are the same. You don't have to copy all the numbers down, but if you are calculating something, you do have to calculate it with all of the numbers. Okay, and now we need to find K. And remember that e to the K equals B. Yada, 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 yada here. And when I do the natural log of this side, I get, of the right side, I get K value. So I'm going to go ahead and do it on my calculator so you can see it, because then I'm going to store it as well. So I'm going to do natural log of 0.87686511017. Enter. That is my K value, and I'm going to store it. So store alpha K. So now that K value is stored into my calculator for later use. And I'm actually just going to write it as K to the T for now, because I found the K over to the side, and I don't want to keep copying it over and over. I am going to write it over here, though. 1318 approximately. We'll just round it over here, but it's not rounded in my calculator. Okay, so now I want to find the half-life, and I'm going to find the half-life. Remember, that is always, you just say 1/2 equals, and then you get rid of the initial amount. So it's 1/2 e to the kt. All right, K is already stored in my calculator. So I'm going to do the natural log of 1/2 divided by K. So the half-life of whatever this radioactive element is 5.275 weeks. Okay, so I just rewrote it in exponential form and divided by K, and that's how I get that. And then part D says how much radioactive material will be left after 50 weeks. Okay, so we're going to set this thing equal to 50. Nope, we're not doing that, sorry. We're going to put 50 in for time. Okay, so we're going to do that, or what we're going to do, we're going to graph it, and you're going to look for the intersection. And the good news is we already have a version of this that we can graph. Okay, I'm actually going to graph this version that we found in the first step. It's already saved in my calculator, and I don't have to worry about it. So I am going to go back to my calculator. Okay, so remember we had it store it in the y equals, so there's the equation. And when I graph it, you can see that it's a good match. And I want to figure out how much is left after 50 weeks. So a couple of issues with the graph right here is that my window doesn't go all the way to 50. So I'm going to change my window so that it goes all the way to 50. Actually, I'm going to 55. Okay, so here's my window. And from the graph, if I want to figure out the 50, I think I can just hit, nope. I have to hit second calc, and I want value. So I want the value at 50. So I did second calc value. I think there's another way to do that, but I can't remember. So 0.145 0.146 or 0.141 is how much is left after 50 weeks. You could also do it this way. So from the home screen, you could go to vars, yvars, function, y1, and then you have the calculator figure out y1 of 50. So this is like f of 50 basically is what you're doing. And you get that same answer of 0.1406. All right, hope that makes sense. Go back and rewatch it if you need to. Oh, shoot, nope, we're not done. I was thinking we were done. All right, here we go. Hopefully this one's a little bit easier now. A colony of bacteria increases according to the law of uninhibited growth. That just means our growth and decay model that we're talking about today. If the number of bacteria doubles in 3 hours, find the function that gives the number of cells in the culture for t. So we just want to make a function. Okay, so we're going to use y equals a naught e to the kt. And it doesn't matter how many bacteria we have. We're going from some amount of 1, let's say, to doubling of 2. So we're going to go from 1 to 2. That's why we're going to write it like that. So we're looking for k here to write the equation. We know it takes 3 hours for it to double. So this is my setup to find k. I'm going to rewrite it in natural log form. So natural log of 2 equals 3k. So k equals the natural log of 2 divided by 3. So therefore, our equation is a equals a naught e to the, and I guess I'll go ahead and calculate a quick decimal to fill in for that. Natural log of 2 divided by 3 is 0.231. But of course, what I really would be doing is saving or storing that value I just found into a value on my calculator. Okay, so this question says, how long will it take for the size of the colony to triple? So now I want to go from 1 to 3, but I know that I know this decay rate. So I'm going to use that that k that I already found, which was that 0.231, and solve for t. Okay, so let me actually pull up the calculator here. Hang on, let me move this out of the way so I can see it. Okay. So I'm just going to take the natural log of 3, and then I need to divide by k, but I did not save k in this calculator, so I have to actually divide by what I know it was, which was the natural log of 2 divided by 3. So instead of me going back and recalculating k, I'm just calling it that, and I am getting 4.755. All right, I hope it makes sense now, although I may check. Oh my gosh. It's like I made the longest worksheet in the world. I don't think I remembered that we had all of these problems. Okay, this is the last one. Hospitals utilize the radioactive substance iodine 131 in the diagnosis and condition of thyroid gland. The half-life of iodine is iodine 131 is 8 days. Okay, if a hospital acquires a sample of 2 grams, how much of the sample will be left after 20 days? So we want to know how much is left if we start with 2 and the half-life is 8 days, but we have to find k first. So we are being asked for this a here, but I don't have the k yet. So I need to see the half-life is 8 days. 1/2 e to the 8k. So I'm going to take the natural log of 1/2. I'm dividing by 8. That is my half-life. I'm going to store it into k. So there is, it's stored into k. So now when I go to solve this problem, says how much of the sample will be left after 20 days. So I'm doing 2e to the, I know the k, times 20. So I'm going to just type it right in the calculator, straight up 20e to the, not 20, 2e to the 20, and k is stored. And I get 0.35354. Okay. Now it says, how long will it take for only 0.01 grams to remain? So I want to know how much is left. So I'm trying to solve, I really like 20 today. Trying to solve for t here, knowing what k is equal to. I'm going to do this one. I'm going to show it on the calculator. I think I'll do this one graphically so that you can remember how to do this as well. I need to move, need to move everything over so I can see it when I have the calculator open. Okay, so to solve this graphically, we go into the y equals. First of all, turn off your stat plots. So go up and hit enter on that button there so that it's not highlighted. And I'm going to put 2e to the k is stored x. Okay, so that k is not a variable. And I'm going to put 0.01 in for y2. And I'm going to do zoom. Let's say zoom. Let's just start with, trying to think of the best one. Zoom standard. That's going to be too big, but we'll start there. Okay. And then I know that clearly I have to go quite a bit off to the right. So I think I'll fix my window. I don't need as much on the x's. And let's go to maybe, I don't know, 50. And I don't need certainly as much on the y's. I only need to be able to see 0.01. So let's maybe go to 0.05 and see what happens here. Okay, so I still didn't go far enough to the right. So now that it's taking me this long, I'm feeling like it would have been a better choice to do this like algebraically. So this is one of those things where you want to play around a little bit with the calculator and decide how much work do I want to put into solving it graphically, or would it be just easier to just go through with the natural log process? All right, so it graphed. Now I can do second calc or second trace here, and I want the intersect, which is 5. And the good news is this is pretty fast. So enter, enter, enter for a guess. And we get it 61.151. So there will be 61. It'll take, sorry, I couldn't remember the question we were answering. So it will be 61.15 days until there is 0.01 left of the sample. All right, officially done. Hope that makes sense. You know, you can always pause and go back. Ask your teachers if you have any questions.